Recording now?
Yes, sir.
Okay. Talking about potential energy. Like you cook in home using CNG gases, natural gas, with in a cylinder. Obviously, it is pressurized, right? So inside the cylinder, the fluid has energy. If you sometimes you see cylinder burst, it burn people due to the fire, also destroy property, right? That means it has a some energy inside due to the pressure. That energy is the pressure energy of the fluid. Now, if this cylinder in the ground floor, then it don't have any pressure energy. I'm sorry, potential energy, because height in respect to ground floor is 0. But the same cylinder you are taking in the rooftop of your house, then you had additional energy, that is kinetic potential energy, right? So this cylinder now have two type of energy. Number one is pressure energy, then it has potential energy. This potential energy normally depend on vertical height, right? So say that height I am expressing letter Z, and P is the pressure. So these two energy we got now in the cylinder. Now, any region, this cylinder is rolling in the rooftop. That means he has certain velocity and rolling around. Then it has some kinetic energy, right? Equal to half m v square. So that means it has some velocity energy, kinetic energy. So what Bernoulli did, Bernoulli is saying that in a fluid system, this summation of these three energy is always constant. And this equation is very powerful equation, and that we will derive. And how actually look like that equation before we derive, we can write over here, it's saying P by gamma. That means pressure by specific weight of the fluid plus V square by 2G. That means actually is the kinetic energy of the fluid plus Z. That means potential height equal to constant. This is the equation. And you can rearrange this equation in different way, like multiply both sides by gamma, then you get P plus B square by 2, then you get rho over here, right over here you get Z gamma, or you can say Z rho Z. So per unit fluid, this is actually potential energy, and this is kinetic energy per unit mass of the fluid, and this is pressure energy. So you look carefully, this equation has three terms, right? So when a equation is valid, all the three terms should have the same unit, otherwise it should not work. So this is a pressure. So this is also pressure. What is the unit of pressure? Pascal, or you can say Newton per meter square. So this one will be the same unit. This one too. That means actually all three is a pressure. So this pressure is called static pressure. This term is called dynamic pressure. And this is called hydrostatic pressure of the fluid. So all summation of all these three is always constant. Okay. So let's we can derive this formula. Before we derive, what is thinking, we are taking a cylindrical fluid element. with area, very small area, dA, and length is ds. And this cylindrical fluid element, it has a cross-sectional area dA, and moving along a streamline. What is streamline? That at any point you make a tangent that will give you direction of the velocity, and fluid particle is moving along the streamline. Now we are considering a cylindrical fluid element. Why is moving upward? What is this? What force? Obviously, there is some force working behind it. Otherwise, it should not move, right? That force is the pressure force of the fluid. So pressure right over here is working on the fluid. And obviously, if it is move upward, right over here, pressure is low. That's why he is moving upward. So I am thinking pressure in the left side is P. So what will be the pressure on the right side? So right side pressure, I am thinking P minus dP. That's why he is moving upward, right? Now, for my simplicity, instead of P minus dP, I can say this is P plus dP. What I'm like to say, the pressure at the two end is not the same. There is a pressure difference, and due to that pressure difference, fluid is moving. That means after derivation, this dP might come negative. Okay. Now, how we'll derive? This is not the static fluid; it is moving. So we will apply your knowledge from engineering mechanics. That means we will apply the Newton's second law in the fluid element. Summation of F equal to ma. So summation of the F, that means force working along the streamline on the fluid element. So we know the left side force is P. I'm sorry, pressure is P. So how much force working in the left side? We know P equal to F by A. So if I multiply pressure by area, we get the force. So left side amount of force working this one, P into dA. dA is the area. Similarly, right side working this one. So you can put in the bracket, then you say dA. Okay, this mass force is working. Now, similarly, if you think one more streamline, there is one more fluid element moving same direction. But there is no, we assume this ideal fluid, there is no viscosity of the fluid. So we'll not consider that one. Okay. Now, you see right now only two forces working in the fluid. 2N only pressure force. And obviously, this fluid element have weight, right? That weight working downward, okay, the W. Now, how we can figure out weight of the fluid? If you know the volume, then you multiply by density, you'll get mass. Then you have mass, multiply by G, you'll get the weight. For example, this one, figure out the volume. Area we already have. Area, cross-sectional area is dA. What is the length of the fluid element? ds. So you multiply by ds, you get the volume. If you multiply this one by rho, so this will be mass of the fluid element. And this one, if you multiply by G, then you are getting W. So this W working downward. Okay. So you see now three forces working in the fluid element. One at the upper end, pushing this fluid element down. Other force P into dA, pushing fluid element toward the upward direction, and the W working downward. Now, this W, this, in streamline, definition of the streamline, the fluid moving along a streamline and along perpendicular direction of the streamline, velocity is 0. Velocity only work along the streamline. So if I make a perpendicular line, this angle is 90 degree. Then W make theta with this perpendicular line, this line. So if this is theta, this W I can divide into two component. Number one, this one will be W cos theta, right? This value will be W cos theta. Other one working along this direction and streamline. And this will be W sin theta, these two components. So now you see in the fluid element, now you have three forces, one working downward, other one working upward, and component of the weight also working downward, W sin theta. And these three forces will push the fluid element along the streamline. So if I take summation of these three forces, sum of force will be m into acceleration of the fluid element. Okay, that will apply. Now all the force we figure out. Now we need to figure out the acceleration. That will show you how you can figure out. Now you see one more thing, that W cos theta. Who is balancing W cos theta? Because fluid element moving along this direction. If somebody should balance W cos theta, otherwise fluid element will move along this direction, because all the force working this direction and W working along this direction, W cos theta, then resultant motion direction will be along this direction, right? So this W cos theta is balancing by buoyant force of the working on the fluid element. Okay. Now we are not think anything about this W cos theta. Our intention to figure out the force moving along streamline of the fluid element. Now this fluid element by certain time is moving from this point to this point. Or if you consider the length of the fluid element, then what will be this height? This height will be dz. What will be this distance? This distance will be dx. Then this length is ds. That we represent with a triangle, because we have value of sine theta. That sine theta we can replace by sine theta equal to dz by ds. We can replace the sine theta in terms of vertical height and horizontal distance. Now, how this angle become theta over here. Theta is showing right over here, right? If you look over here, this is W working along this direction, right? So how much this angle or how much this angle? This angle is 90. Then how much this angle? You look over here, W make with angle with this line is theta. So this is theta. Now in this angle, you see this is 90. This is 90. And this angle how much? 90 minus theta. So obviously this angle will be theta. Okay. Now we'll apply the second law, but before that, we need to figure out the acceleration. So this fluid element moving along the streamline. If distance travel by the fluid element, if I say function s, this is ds. ds means small segment of distance. So if this is s, then the velocity of the fluid element v is function of s and t, distance and the time. From this relationship, we'll figure out the acceleration. What is our acceleration actually? dv by dt equal to acceleration. So this value we need to figure out. What is dv by dt? So what is that one actually? If you have f function of xy, then how you figure out the value of df? By applying the math differential equation that you already learned in first and second semester. Okay. Right over here, just showing all the angle and the free body of the force that I already discussed it. Okay. Now, that was my question, that how will figure out dv by dt. You see right over here, I put a cross sign, then big circle. That means this is not part of the derivation. Just I trying to show you that how we can figure out the acceleration. This is the side note. So f equal to, this is a function of, you see, four variable. Then how you can figure out the df? df equal to, first you make derivative with respect to one function, df by dx into dx. Then you figure out df by dy into dy. Similarly, you have function z, df by dz into dz, then t. Now, the velocity of the fluid particle is a function of s and t. So I can say v equal to fs into t. So what will be the dv? dv equal to, you see, df, that means del v by del s into ds. So you're getting one term plus del v by del t into dt. Okay. Now this equation, if I divide both sides by this term dt, then what are we getting? We are getting dv by dt equal to del v by del s into ds by dt, right? Plus, you get this term dv by dt. This dt will be out. We're getting dv by dt. Okay. Now you see this term dv by dt. in partial derivative of velocity. This will be zero because we think that the flow is steady flow. So there is no local acceleration. So we'll assume this is zero. So this term, what is this term actually? Acceleration, change of velocity with respect to time. So this is acceleration equal to is coming dv by ds into what is this term? Change of distance divided by time. That means velocity. So this acceleration equal to velocity into dv by ds. That means you see velocity is changing along the distance, but not with the time because we consider the steady flow. So local velocity with respect to time is zero, but velocity is changing along the distance s. That's why dv by ds is not zero. So this is our acceleration. Now we can easily apply the Newton's second law. Same thing, we just figure out the velocity acceleration right over here. Okay. So let's go in the next slide. Right over here, we don't apply the Newton's second law. Just show you how become as equal to dv by ds. That's what we're showing over here. Now, right over here, we'll apply the Newton's second law. So how we can apply? You take summation of force working along the streamline, this direction. So in the bottom, P into dA, this is the force. So this is our first term. Then P into dP dA working downward. So minus this term. W sine theta working along this direction, downward. So minus W sine theta equal to M into AS. Now M remain like that. What is the AS? AS equal to V into dBs. Now what is the W? You figure out the volume, cross-sectional area into length, into G, rho into G. That you are getting the W. That W will be over here. And how much will be the mass? Mass will be accept the G value. That means mass will be this mass. That mass will put over here. And sine theta will replace sine theta equal to dz by ds. And then we'll simplify the equation. So same line, we put it over here. Now, if you simplify this line, then you see PDA will be out. So in the left side, it remain only P into DA, this term. Now, what is the W? W equal to rho G dA ds. I already show you. So this is our W. What is the sine theta? dz by ds. That is showing over here. What is the mass? Just rho into V. So rho V is the d into ds into rho. That is mass. So this mass is the mass. And what is the acceleration? We already got it over here. This term, we put it over here. Now we'll simplify. And if you look carefully, right over here, this ds will be out. ds will be out, right? And you see all the term has dA. This dA will be out. So in the left side, we have dP minus rho G dz. In the right side, we have rho V dV. Now see, if you take the integration right over here, you get minus P. Minus right over here, you are getting rho GZ. GZ equal to, on the right side, V dV. You're getting rho into B square by 2. Then you take all of them in the left side, there is a constant, right? So all this term will be equal to coming constant. So let's see on the right side, right over here. We take the integration, then we are getting this term. Over here is something wrong, that this rho will be not be here. Both sides we divided by rho, dp by rho, v dv, g dz. This row is out. Now you take the integration. So you're getting p by rho, v square by 2, d, g into z. So you're getting this equation, this one after integration. And for incompressible flow, rho is constant, right? That's why rho is not part of the integration. Finally, you multiply both sides by, again, by g. Then you're getting p by rho g. B square by 2g, right over here only z. So you're getting this term. P by gamma B square by 2g plus z equal to constant. Now, if you apply this equation between 2 points of a fluid system, say you have a pipeline and natural gas coming from Kumilla to Dhaka. And this point, you know the value of P, say P1 you know, V1 you know, also Z1. That means if you have elevation of the pipeline from the ground, say Z1 you know, this will be Z1, vertical height of the pipeline. Because when you transmit something through a pipeline, you cannot keep it horizontal due to the terrain of the land, right? Sometime you need to pass the pipe under the river or might be top of the hill. So you get value of Z1. Now, I like to know how much the pressure over here, how we can figure out. We can put a pressure gauge, then you can figure out, right? But I don't want to the pressure gauge. I look at the drawing, I know right over here diameter of the pipe, say D2. I look in the drawing, I see diameter of the pipe over here, D1. Now, right over here, I have some equipment, then I can, or pressure gauge, I read the pressure, that much. What is the velocity of the fluid I'm getting from pitted tube is this much, vertical elevation I know. These three terms I know. But I need to know what will be the pressure over here instead of putting any equipment. Say you have distance 10 miles from first point to second point. Now, how we can figure out? This is second point. You see, for point 2, I can figure out the Z2 by looking to the drawing. That what is the height of the pipeline from the ground level. It might be 0 or might be 1 feet or 6 inches. It's different. Now, how will get the velocity? I know velocity at point 1, but my target figure out pressure, right? So if I apply this equation, you see at point 1, P1 I know, V1 know, Z1 I know. Specific weight of the fluid I know, what type of fluid is passing, right? G I know. V2, Z2 I know. My target to figure out the P2. Now, if you know the V2, you can figure out the P2. But how we can figure out the V2? We know our continuity equation that Q equal to A1 into V1 equal to A2 into V2. So A1, V1 you know, A2 you know from the diameter pi by 2 pi by 4 d2 square. For point 1 pi by 4 d1 square. So you get V2 from here. Then easily you can figure out the value of P2. That is the beauty of Bernoulli's equation. So in Bernoulli's equation, it's saying summation of all three is constant. Say 1 point, we have three value, right? Three part. So I am saying this is 60, this is 40, and Z20. So what is the summation is coming? Summation coming 120. Okay. Now, when fluid coming at point 2, velocity is reduced to 10. And Z coming, say, 20. Then what will be the summation of all three in the right side? As per Bernoulli's equation. Anyone? Hello?
100.
100?
Yes,
Okay.
yes, sir. The right side will be 100 to equal the
Right side
left side.
has to be 120 because summation in the left side summation is 120, right? 60, pressure is 60, velocity 40, Z1 20. So left side coming 120, right side has to be 120. Now my question, how he'll make 120? Because right side Z value, potential energy, you got 10. Kinetic energy, you got 20. So how much will be pressure then? To make 120, pressure has to be go up. It will be 100. You understand?
Yes, yes.
That means any situation, the summation of these three has to be constant. What does it mean? Say you are working Dhaka City Corporation as a mechanical engineer. You working in a pipeline in that carrying water from Jamuna River to Uttara city. Okay, point 2 is the Uttara. So at point 1, you have energy of the fluid. Say you right over here, you have a multiple pump. So you know you can figure out energy of the fluid at point 1 by using this Bernoulli's equation. Say you got 500 summation of all three. How much will be summation of all three at point 2? Theoretically, anyone? Has to be same. At point 1, energy of the fluid is 500. Then it will be same at point 2 as per Bernoulli's equation. That means energy of the fluid, summation of all three is always constant. That Bernoulli is saying. So that means at point 2 also will have energy, total energy 500. But in reality, it is not possible because when fluid flow through the pipe, there will be frictional loss in the pipe surface. And say velocity of the fluid, or right over here, 30 meter per second. Right over here, you will not get 30 meter per second. So there will be some loss that is called frictional loss. That is not counted by Bernoulli's. But still, this is a very powerful equation, and you will see everywhere we'll using it. Okay, and later on, and we will make some correction in the Bernoulli's equation by adding the loss. Okay, so let there is a different form of Bernoulli's equation that we see that how many form it has. Okay, so this equation sometime we instead of if someone asks you the what is the Bernoulli's equation, you can say p by gamma b square by 2g plus z equal to constant. That is, it seems like you are just reading letter, some letter, but uh, you can describe it in terms of pressure, in terms of energy. So Bernoulli's equation, this term, first term, P by gamma, is called static pressure or pressure energy per unit weight of the fluid. B square by 2g is called kinetic head. So you see is coming pressure head, kinetic head. And Z is called potential head. So you can say summation of pressure head, velocity head, and potential head is constant. That is the Bernoulli's equation. And now somebody say, give me a job interview. They ask you, what is the Bernoulli's equation? So if you directly say P by gamma plus B square by 2G plus Z equal to constant, that's okay, but is not 100% right. You're supposed to say summation of pressure head, static pressure head, kinetic head, and potential head equal to constant. That is the Bernoulli's equation. Then he said, write down the Bernoulli's equation. Then you can write down this term. That this is my Bernoulli's equation. Okay. Same thing right over here. What we did, we just rearrange the Bernoulli's equation. How? This is Bernoulli equation. Both sides you can multiply with the gamma. So ultimately, what you getting? You see P equal to this one. That means all the three terms you can express in terms of pressure. So P is the unit is pressure. So this will be also pressure. If you put all the unit like rho kg per meter cube, G is meter per second square, Z is meter. Then you simplify, then you see this is also coming kg per meter cube is the rho, right? Then you multiply by G, meter per second square. Then you multiply by Z, unit meter. Then you see this unit ultimately coming in the bottom. You have meter square. If you take this meter, meter is out. So you will have kg, then meter. I take 1 meter divided by second square. Then still in the bottom, you have meter square. This one. So kg meter per second square is the Newton. So finally, you are getting Newton per meter square. That means this is also pressure. Similarly, you can check this one, you will see you will getting Newton per meter square. So in terms of pressure, you see right over here, we describe Bernoulli's equation in terms of head, static pressure head, kinetic head, potential head is summation is constant. What will be right here? What will be unit of P by gamma? B square by 2G. In same up unit of Z, because this unit Z particle height, meter or feet. So unit of this term will be the same, meter or feet. P by gamma will be also meter or feet. Similarly, if we like to express Bernoulli's equation in terms of pressure, then what will we have? That is showing over here. That P is called static pressure. Rho v square by 2, dynamic pressure. And this one, hydrostatic pressure. If somebody say summation of static pressure, dynamic pressure, and hydrostatic pressure is constant, this is the Bernoulli's equation. This is also is the right statement. Okay. Now, you see, right what we are saying that in a fluid, summation of static pressure P, summation of dynamic pressure, and summation of hydrostatic pressure is constant. Now, how we can measure it? Hydrostatic pressure, rho g, easily you can measure by measuring vertical height. Now, how we can measure the velocity and how we can measure the pressure? Measure the pressure, you can use pressure gauge, you can use manometer, right? But how we can measure the velocity? That we'll figure out, okay? So, to measure the pressure, we already study manometry. There is one thing you can figure out by static pressure tab. Just make a hole in the pipe. You can figure out the pressure. We'll explain it how. Then you can use pitot tube. We'll explain it what is the pitot tube. Then you can use the piezometer. So what is the piezometer? You see, this is a pipeline is flowing from Jamuna river to Uttara. Somewhere you make a hole and you attach a tube, vertical tube. Then what will be happen? The inside the pipeline there will be pressure. So fluid will try to come out through the tube and the atmospheric pressure try to push him down. If inside pressure is higher than the atmospheric pressure, then this height will be increased. But if pressure is coming down, then what will happen? This height is gradually coming down because atmospheric pressure will push him down. So this is the piezometer. This way you can measure the static pressure of the fluid. That means only value P. Similarly, you have a inclined pipeline, you can put a piezometer like that. Okay. This kind of equipment you can use if pressure of the fluid inside is not that much high, but if the pressure is extremely high, then you need to use manometer. How? So, for example, with this one, if I attach a rubber tube with this hole, let's say I'm attaching a rubber hole like that. Say upper I keep opening, and inside I put some denser fluid, say mercury. Then if this pressure is too high, then fluid is come over here. But to push the mercury upward, he need to have more higher pressure. And right over here, there will be atmospheric pressure. This way, you can measure the pressure. Okay, that we already learned in the manometry chapter. Now, what is the pitot tube actually? Pitot tube is a L-shaped tube. Is a L-shaped tube, and it has a little hole at the front. At the front, sometimes they have a hole at the side. Okay. So at the front, say air or fluid coming through the opening, it directly coming through this S, right? But right over here, fluid will stop. If fluid will stop because there is no flow, then what will be happen? say you have a river right over here, water coming in the river. Right here, you make a dam. What happened? Why height, water height at the dam is going upward direction? What is the reason? Because fluid coming with certain velocity. It has velocity kinetic energy. V square by 2g. It has pressure. It has elevation, z. Three energy coming with three energy. But it's coming to the dam, then you stop him. That means his kinetic energy will be then converted into pressure energy. Because you force him to stop, where will go that energy? Okay. Uh, could you hold down just okay? I was trying to explain that how Peter tube work. So what happened? I'm saying that if you stop the flow of a pipe, what will be happen? His kinetic energy will be immediately converted into pressure energy, and it will increase the pressure more, and your pipeline might be get burst. For example, fluid is coming right over here, so it has three energy: P, V square by 2g, and also Z, P by gamma, right? So you coming over here, you have a bulb. Certainly, you close the bulb. Then what will be happen? It has energy coming with P by gamma, but V square by 2g, this much energy will be immediately converted into pressure energy. And certainly this area pressure will be increased more. So that means this area will show summation of two pressure, the static pressure and also dynamic pressure. This total pressure is called stagnation pressure. So in P2 tube, when fluid hitting the edge of the tube, right over here, pressure will increase. That means that pressure will be stagnation pressure. But right over here, there is a hole. And this is also tube with the blue line. This is also tube, okay? So in the right over here, this pressure will be only static pressure because fluid is still moving. So pressure in this tube and the middle tube is not the same. So if you attach a tube with the outside tube and with the middle tube, and then you put some manometric fluid, then you apply some formula. You can measure the velocity of the fluid. Okay. Similarly, for example, in aircraft, when it is fly, how you know what is his velocity? At the nose of the aircraft, they put pitot tube, this kind of things. Okay. So aircraft flying at a certain speed, you can think opposite way, that aircraft is static, but air coming with the flowing over the aircraft with higher speed, with same speed. If this is moving, say 140 mile per hour, that mean air passing over the aircraft with 140 mile per hour. So it's coming in 140 mile per hour, is hitting the PT tube, then it is stopped. And from the pressure difference, and obviously it is giving converted the data digitally, and pilot can see the speed of the aircraft. Okay, this is the example. Similarly, if you have a wind tunnel, in the wind tunnel you like to measure the air velocity. So if you put a pitot tube and add the manometer, you can measure the air velocity. And in our wind tunnel in the lab, they have a pitot tube. Now, I need to show you that how actually pitot tube work, how you can measure the velocity by using pitot tube, and what is the stagnation pressure. Stagnation pressure mean already fluid have a pressure. That means pressure at the dam. Say this is the dam on a river or canal, water is coming with this direction with 3 energy, right? But coming over here, velocity you stop it by forcefully. So that kinetic energy right over here is converted into pressure energy. That means this fluid have two pressure. One is static pressure, other one is stagnation pressure. Not stagnation pressure, that means pressure coming from the kinetic energy. Summation of these two is called stagnation pressure. So why you needed the stagnation pressure? Could you stop just 1 second? Let me just pause directly. Okay. So what I'm saying is somewhere, if anyway you stop the motion of the fluid, then kinetic energy will be converted into pressure energy. So that pressure energy and the when it's coming, it originally has some static pressure. Summation of these two is called stagnation pressure. What is the useful? Say you are working in a irrigation. In our country, we don't have that much land, but like in the US, and if you ask someone that what do you do for living, he will say, I have a very small farm. What's the size? He will say 100,000 acre. Okay, that means huge kind of a city. So 100,000 acre of land, he has a farm. Obviously, the land is not even. So they might have a canal, and also they use a small aircraft to spraying the medicine in the crops. Okay, so if you design the irrigation canal, so irrigation canal you designing, and somewhere you need to protect the water. So you don't want that water cross this line. So what will do? You will make the dam with some gate, right? Now how will figure out the size of the dam? What will be if you use the material like some steel plate, you need to figure out the design that steel plate. What will be the thickness? What will be the support? How much will be the force there? So what do you need? At first, you need to know what will be the stagnation pressure, because fluid is coming with certain velocity. All V also have static pressure. Then you coming over here, it will have same static pressure plus this much kinetic energy will be converted into pressure. So it is giving increasing the pressure. So this pressure is stagnation pressure. So if you know that stagnation pressure, at least at initial stage, you can figure out that what will be my size, what kind of material I can choose to design that dam, okay, or to protect the gate or to protect the water. So that is the application of stagnation pressure. Now we need to know the how you can figure out the stagnation pressure. So you see there is a real picture of uh, pitot tube. So you see there is a hole right over here, and when fluid coming along these edges, fluid velocity stop. So the right over here, the pressure will be a stagnation pressure. This is static pressure. So if you attach a pitot tube between right over here, if I make this one, this is this tube, and I'm attaching with this tube. Then you have some difference of manometric height of the fluid. From that difference, you can measure the velocity. For example, forget about this hole. You just put a something right over here with very narrow hole like that. This one right over here. So fluids coming around this hole immediately will be stopped. Some fluid will go through this line. It's possible, right? But he'll immediately stop due to the L shape. So that's why right over here pressure will increase. It become stagnation pressure. But if you make a hole in the wall, that will be, it's called tap, static tap. So there will be static pressure. So now you add a rubber tube. We put some water, or you can use mercury or any other fluid with the color. Then what will happen? If pressure both end is same, then this manometric fluid will be same level. But when you stopping the velocity over here, pressure over will be high, over will be low. Then the height will left side is increase. So you get this difference, this much distance. By measuring this much distance, you can measure the stagnation pressure. Okay. I miss one thing, that what is the static tap? Static tap mean you have a pipeline, you make a hole over here. What happened? If inside the pipe is pressure is higher than atmospheric pressure, then fluid will come out. But if pressure is lower than atmospheric pressure, then it will not get out from the pipe, because in due to the inside pressure, fluid try to move through the hole. But outside pressure is more than this pressure, then he'll try to push him down. Okay, this is the static step. So sometimes they use static step to connect the manometer tube. Okay. Now let's see how we can figure out the stagnation pressure from the pitot tube. Okay. These two graph I'll discuss later on. Okay. This is interesting. You see the pipeline I took from the website from some company. You see Canada and US, they're trying to build a pipeline from all the way Canada to Texas. Similarly, Iran tried to pipeline from Iran to Afghanistan, Pakistan, then China. Also, they're now trying to include India. So you see, all the pipeline elevation is not the same. Now, how we can check this pipeline? If you have a drawing, you can check it. Otherwise, what need to do? You can drive along the pipeline if you have a road, or you can use a small helicopter, fly from, say, this is border of Iran, then fly over the pipeline and you go to the border of, say, Afghanistan or Pakistan to check the pipeline, how it is going under the hill or top of the hill, and you need to figure out which portion will be pressure will be high, where will be velocity low, right? In that case, what need to do? You need to use either a helicopter or you need to use a car, but both is expensive. And say you are working for Halliburton company, and some boss visiting from US, your office in Iran. Now he will stay only for 3 hours, and he like to know the which portion of the gas line is more critical. Where is the highest elevation? Where is the lowest elevation? How you can show him within 3 hours? Only possible if you have a sketch drawing and if you have a graph. Okay. I'll discuss after discuss the P2 tube. Okay, so let's see what is the stagnation pressure. Sum of static pressure and dynamic pressure is called stagnation pressure, because in Bernoulli's equation you can express it like that: P plus rho v square by 2 plus rho dz equal to constant C. Now these two terms, that means static pressure plus kinetic pressure or dynamic pressure, is called stagnation pressure. This is showing over here. So it's saying stagnation pressure represents the pressure at a point where the fluid is brought to a completely stop, and isentropically. Isentropically means entropy constant. No energy is getting out from the fluid, no energy getting inside of the fluid. Okay. So this is the definition of stagnation pressure. Now, how we can measure the stagnation pressure, that we will discuss over here. Okay. Say there is a flow going this way, and in the pipeline and the upper end, you put a static piezometer. You make a static hole, then attach a rubber tube. This is called piezometer. And right side, you put a pitot tube. So right over here, when fluid coming, velocity will be 0 at the pitot tube, right? And here, pressure will be high. Then fluid will go through the tube, try to flow upward. But atmospheric pressure try to push him down. Similarly, when you make a hole, the fluid is try to go upward due to the which pressure, due to this component, static pressure P. But atmospheric pressure try to push him down. Now, why right side is a little bit going more height? You see height of the fluid inside the tube, this mass is higher on the right side because due to the stagnation pressure. Okay, because pressure at point 2 higher than point 1. Point 2 pressure actually is summation of these two. That means P plus rho v square, summation of these two. But at point 1, pressure only P, because fluid has all the energy, but when it's coming point 1, is still moving with kinetic energy. So he'll not giving the kinetic energy at point 1. For example, you have two bags. On hand, you have some candy, say pressure energy. Right hand, you have some apple. So coming at point 1, you are just leaving the candy. Apple still, you drop the candy, but with the apple, you are still moving. That means right over here has only static pressure. So that's why over here pressure is low. Height is not that much, but at point 2, pressure is increases. That's why fluid is moving upward more. So that's why saying that this mass portion height of the fluid, that means actually equal to b square by 2g. Because this static pressure is this mass height, and this mass height is the dynamic pressure. So total pressure is making increase of height this mass. Okay. Now we will apply the Bernoulli's equation at point 1 and 2. Then we'll see what is how look like. So if we Bernoulli's equation, there is a, you can use this one too, that P by gamma plus B square by 2G plus Z1 or Z equal to 0. You can use this equation. But instead, I use the other one. Multiply both sides by gamma. Then you have this one P by rho B square by 2 plus Z rho G equal to constant. Now, I apply this equation between these 2 points. So, at point 1, what do we have? I have P1, static pressure. I have V1, right? P1, V1, and obviously Z, point 1 and 2 will be same. So, but at point 2, velocity is 0. So, this is equation I apply between point 1 and 2. Now, we see point 2, velocity is 0. So, velocity turn will be 0 this turn. Now, Z1 and Z2, they are same horizontal line. So, these two will be out. And this P2, we call it stagnation pressure because you forcefully stop the flow. So, this P2 will call it PS by P stag. Now, you figure out the V from here. So, V1 square by 2 rho will be equal to P2 minus P1. That means P stagnation. Now, you simplify, you get this one. So, any region, if we are able to measure this difference, P stag minus P, you are able to measure the velocity of the fluid. And how we can measure it? Again, if you add a rubber tube, if you right over here, then you can measure this deflection. Say right over here, you use some mercury. So obviously right over here, pressure is more. So this mercury will push him upward and this will go down. So how much the difference, pressure difference is this much distance from this line to this line. So from here, you can measure this difference, P stag minus P, and put it over here, you get velocity of the fluid. So let's see how we can measure it. We will apply the manometry that we learned before. Okay. So how we can apply the manometry? We will figure out the pressure at point 1 and at point 2 by applying manometry. So let's figure out the pressure at point 1. So what is the depth of point 1 from the free surface? This mass depth, right? So P1, this is my P1. So I am saying P1 equal to, I start from the top. At the top, atmospheric pressure working right over here, downward, right? So P atmospheric pressure right over here plus height from here to here. So first take H1. Our fluid, same fluid. So H1 rho Fg. Then plus this mass height, H2. So H2 rho Fg. What I did, the total height just divided in some segment. We are saying from here to here is H. This height is H. And then from here to here is H1. And from the pipe surface to P2 tube and point 1 is H2. That's for simplification. So we figure out pressure at point 1. We get this much pressure at point 1. Now we'll figure out the pressure at point 2, P2. P2 means P stagnation. So instead of P2, we use PS. So start from the top, right over here, atmospheric pressure. So atmospheric pressure plus is coming down. So you need to add the pressure plus H rho G, this mass height. Then coming down by H1 rho Fg. then coming down by H2, then H2 rho F G. Now you subtract these two, PS minus P1. Then you will see this term will be out if you make subtract. Then H1, this one will be out. P atmosphere will be out. So PS minus P1 is coming rho G H. So what is rho G H actually? This height, this portion of the fluid, right? If this is the, right now is showing same fluid, if you attach a manometer, this height will be manometric fluid, okay? Now, uh, if you apply Bernoulli's equation between right over here, or this PS minus P1, you put it over here, right over here, equal to what the value? Rho G H. So if you put this difference, so 2 rho G H divided by rho, root over. So rho will be out. So you are getting 2GH root over. That will be your velocity of the fluid. Okay. Now, if we go in the previous slide, you apply Bernoulli's equation 1 and 2, similarly previous way, you get this one. Then V1 square by 2G, PS minus P1 by gamma. Now, this gamma equal to rho G and PS minus P1. PS minus P1 equal to rho G divided by rho G. Now, if I attached a tube in the manometer, say inside going water. So this will be gamma water. So this will be gamma water. Right here will be gamma water, right? And this deflection, instead of we have the same fluid, but if you put mercury, then your deflection will be this much. Then this difference will be right over here will be rho mercury, rho m. This will be rho m. In that case, your Gg will be out. Then there will be one more term, rho h into rho m divided by rho water. I can say rho m. That water is flowing inside the pipeline. But if you are using same fluid in the manometer and also in the tube, in that case, these two will be out. Rho m, rho f will be same. Then you have only H. And finally, V will be root over 2GH. Okay, clear? Any
sir.
question? Yeah, go ahead.
No, sir, no question.
No question. Okay. Okay, now let's go back to that I was trying to explain you with the pipeline, that without visiting the pipeline, how we can give answer to your boss or a technical committee that here is the my drawing of the pipeline, here is the my all the pressure energy, here is the this much is the hydrostatic pressure, this much is the elevation. So you don't need to fly in a helicopter or in a car. You just look in the graph. So what is that graph? So there is a two thing we use in the pipeline system. Number one is called hydraulic grade line. This one is called hydraulic grade line. Other one is called energy grade line. So energy grade line sometimes is called EGL or energy line, and hydraulic grade line is called HGL. So what is hydraulic grade line? In the Bernoulli equation, you see we have uh, three part, right? If you write down again, to it will be clear. P by gamma plus b square by 2g plus z equal to constant, right? So if you take summation of P by gamma, that means static pressure, and the elevation Z, that means P by gamma and the Z. Obviously, these two terms should not be same all around the pipeline. It will go up and go down. That I show you the slide, that how a pipeline look like. So in that case, every point, for example, every point you measure these two terms. So say you measure right over here, right over here, right over here. You see right over here is going down. Similarly, right over here is going down. So you take several points, you take that data, okay? Then that data you plot in a graph. So you put in a graph, then your HJ line, this is your reference line, elevation in the bottom. Then all three and a summation of two energy, you put your starting point, then it might be gradually come down. Right over here, it is again increasing, right over here decreasing, and I make a line. Then join this line. So this line is called hydraulic grade line. Okay. Now, which one you are missing? Kinetic energy line, like V1 square by 2G. So in Bernoulli equation, you take two terms. Other term is V1 square by 2G. So every point in your pipeline, if you know the velocity, easily you can figure out velocity. How? By using Bernoulli equation. You look in the drawing, you know the your what I'm saying, your pipeline going zigzag way by different orientation. Okay, right over here, you know the Q flow rate, you know the area of the pipe, you know diameter, you can find the area. So you can figure out the V. V will be Q by A. Why? By contour integration. That Q equal to A into V equal to constant. So you can say A1 into V1 into A2 into V2 equal to A3 V3. So if you know right over here, you know diameter of the pipe, you can figure out the area. So right over here, your equation A2 V2. Right over here, A1 B1. You just say both same. Then you figure out this value you know at the beginning. A1 you know, B1 you know, A2 you know. So you can figure out the V2, right? If you know V2, then at one point you figure out the V1 square by 2G. So that will be this mass. Say right over here, you got this mass value. So you just add top of your hydraulic grade line. And right over here, you got this mass V1 square by 2G. Right over here is this mass. Then you got the several point, this point right along the line. Then you make a line. So this line, what is this line represent? Top line. It representing the total energy. Number one thing, it representing if you counting, say right over here, you're checking right over here. So how much your hydraulic grade line distance over here? So hydraulic grade line energy will be this mass. How much the kinetic energy? This mass. So what will be the total? this much from here to here. So the top line is represent the your energy line, total energy. Okay. So hydraulic gate line, the line that represent the sum of static pressure and elevation head is called hydraulic grade line. And right over here, other one, energy grade line. The line that represent the total head, that means whole quantity of Bernoulli equation, that is called energy grade line or energy line. The difference between EGL and GL is equal to dynamic head. So say, for example, this mass your EGL, okay? You subtract the hydraulic portion, then you get dynamic portion. That means B square by 2G. Now, you see this line coming downward. Why? Actually, as per Bernoulli's equation, that this energy has to be constant. And show the example, the 120 second point will be also on 120. So it travel through fourth point, there will be also 120. But theoretically, it's possible. But actually, it is not. Because Bernoulli did not consider friction of the fluid between the pipeline or between the system and the fluid. So that's why in reality, in ideal condition, this line, total line is coming downward, but it has to be horizontal. So this blue color line is called ideal or theoretical energy line. But due to the friction, this line is gradually coming like that, or might be going like that. Depends on what type of fluid, what type of pipeline or fluid system you have. Okay. So this is called, the red one is called real energy line. That's why, say you are transferring natural gas from Kumulia to Dhaka, and you put only one pump in Sylhet or in Kumulia, it be able to carry the natural gas in Dhaka city? No. So in multiple point, you need to put multiple pump to overcome that frictional loss. If there is no friction in the fluid, then say you are carrying natural gas from Iran to China, say about 800 mile or 1,000 mile away. So one pump will be enough. You put just one pump, all the way fluid will flow. There will be no loss, but it is not possible. Okay. So from here, you will learn the derivation of Bernoulli's equation, then different form of Bernoulli's equation. You learn what is the stagnation pressure, how we can measure, how you can apply Bernoulli's equation to figure out the velocity of the fluid. Then you need to learn what is energy line, what is the hydraulic line. For definition, if I put these two in exam, then at least you show the definition, then show it by a graph and by a sketch. Okay, so any question from here?
No, sir.
No question? How much time we have? We have 3-4 minutes, right?
Yes, sir.
Okay. So no question. Are you able to follow my class?
Yes, sir.
Yes. Okay. Okay. Good. In the next time, we'll solve some problem. Okay, related to the Bernoulli's equation, and that will be interesting. So just keep in mind that Bernoulli's equation needs some correction because he didn't use the or consider the frictional loss of the fluid. Okay. So we can stop it here. So far, any question?